we have 2 invited talks and 3 lightning talks. So first one is by Liang Zhi-Chao. So now, yeah, Liang, please, the stage is yours.
Okay, can you hear me?
Yes.
So I'm going to talk about the evolution of high-latitude m=1 observed in the direct Doppler signals over the past 5 solar cycles. So in the 1990s, there are evidence about the high-latitude oscillations reported by Ulrich using Wilson Dopplerograms. And so Ulrich computed the zonal velocity by averaging the v-loss over longitude weighted by sine longitude to get this a proxy of zonal component of surface Doppler zonal component of the surface velocity at this, and on the left is the synaptic map of this zonal velocity, and the major feature is the torsional oscillation with a 11-year period. So it's this band migrate toward the equator, and at high latitude, there's oscillations in this v-zonal velocity with a period of about 34 days. So it's reported as very long-lived wave patterns and polar crossing flows. So, and the amplitude is about 7 to 10 meter per second. So this is a proxy. So it's not really V5 component. And then, so we apply the same analysis to Wilson, Gong, and HMI Dopplerograms. And here's the synaptic maps from the 3 data sets. And the top rows is the overlapping time period between the 3 instruments. So you can see the same patterns at high latitudes. And the bottom are the other, another overlapping time period, and you can see the same feature. Oh, so here we filter out the 11-year oscillations. So there's no torsional oscillation here. It's just high latitude oscillations. Okay. And then we, to better compare the results, we compute the high latitude band average. And it's also north-south anti-symmetrized because the main component is the anti-symmetric component. It's anti-symmetric in V5. And we can see that they are consistent to a great extent. Like the middle one, we have all 3 instruments during the overlapping period, and they are all consistent. And then we compute the power spectrum from this high latitude band average over a 3-year time window. And we can see the excess power at this frequency, 33A. It's visible over past 5 solar cycles. So it's observable almost all the time. And this frequency corresponds to this minus 86 nanohertz in Carrington frame. So it's corresponds to the high latitude m=1 mole in JSON 2021. So here we don't do any spatial Fourier transform. So it's just, it corresponds to this m=1 mole. And then we also compute the spectrum for other latitudes, lower latitudes, and we can also see the mole, it's visible at lower latitude. maybe not early Mount Wilson, but in HMI it's clear that it's at multiple latitudes. And this is another comparison between different instruments. So this is the spectrum during the overlapping period. So Gong and HMI, they are just like on top of each other. And the line width is about 5 nanohertz. So it corresponds to a lifetime of 2 years. And the period in the Earth frame is 34 days prograde, or it's 134 days in retrograde in the Carrington frame. And so, okay, so then we want to know how they look like on the solar disk. So we align the solar images and then apply a frequency filter around this mode frequency. So there's no spatial Fourier transform, just frequency filter in time. And you can see it's the pattern, the spiral pattern at high latitude. And polar crossing flow, you can also see because this is line of sight Doppler signal. So this signal, they are polar crossing flows over 10 meters per second. And the pattern, sorry? And the pattern, they are north-south antisymmetric. So you can see blue and here's red, here's blue. So it's mostly north-south antisymmetric. And on the right is the ring diagram horizontal flows project to line of sight. So and you can see that it just they are very consistent. This implies that because we only have horizontal component from the ring diagram, and they are consistent, implies that the radial component of the mode is not significant. And they are very consistent, like even at low latitude, this pattern, they are all the same. Okay, so we have this power spectrum from 3-year time window, so we can measure the total power and the frequency of the mode. And so here on the right, this is the mode frequency from 3-year window and windows, and the shaded area. So this is the orange is from Wilson, green is from Gong, red is from HMI. So during the overlapping time period, they are on top of each other. And the blue is the rotation rate at high latitude, surface rotation rate. And this is sunspot number. And the vertical bar is the solar minimum. So we don't see a clear 11-year periodicity in the frequency. If you only check the HMI, you may see this and it corresponds to this. So maybe if you only have HMI data, you will say, oh, it's a positively correlated with the sunspot number. But if you look at a longer time series, then it's not obvious that there's a correlation between the frequency and the sunspot number. And the correlation between the frequency and the blue curve, the surface rotation rate, you can see the long-term trend. They both have this long-term trend. Okay, and so this is different from the Rossby modes. So the Rossby mode is not, they have negative correlation with the sunspot numbers. Okay, and the next is the mode amplitude from these 3-year time windows. So you see the mode amplitude. It peaks during solar minimum. This is vertical part, solar minimum. Yeah, but not always at solar minimum. Like here, it peaks at the rising phase, Here is also rising phase, and here is again solar minimum, solar minimum. So it's not always solar minimum. So this negative correlation, it's not like very minus 0.9, but it's just 0.5 because there's a time lag sometimes. So it's kind of nonlinear. But we also compute a correlation with the high-latitude rotation rate. The negative correlation is much higher than with the sunspot number. Okay, and compare with the equatorial Rossby modes. So for the Rossby mode, it's positive correlated with sunspot number, while the high-latitude mode is negative correlated with the sunspot number. So for high-latitude mode, the magnetic field suppressive, but for the Rossby mode, it's positive correlated. Okay, so I stop here. I stopped earlier. So okay.
Okay.
Yeah.
There is time for lots of questions.
Yeah.
So yeah, please ask a few questions.
I have maybe a small comment.
Yeah, please.
Possible. I heard Roger saying that he couldn't see the Rossby modes in his data. I believe that Zhi-Chao,
Yeah.
at least in the HMI data set, you can
Yes.
see in the V zone a few modes, but of course they are very, very low amplitude because they are at low latitude. So when we do the projection onto the line of sight, there's not much left. Yeah.
Yes.
Can you say some more about this? Or?
Right, because I can only see the very low M modes because this weighting function is optimal toward the M equals 0 actually. So M equals 1 is strong and 2 is weak and 3 is almost gone. So I can see M equals 3 Rossby mode at here. It's a V5 component because mostly it's V theta for Rossby mode. So in V zonal, it's even weaker. So it's I remember it's at this latitude, I can see M equals 3. I mean, I don't do spatial Fourier transform, so there's no EIM5, but the frequency corresponds to the M equals 3 Rossby mode. And I can also see other M equals 2 critical latitude mode, for example. Very low M modes, yeah.
Do you remember the frequency?
Yeah, it's like within 1,000 nanohertz, I can see a few modes.
Yeah, but this is outside of this plot, right? Oh.
Yeah, it's outside of this plot. Yeah.
Okay, because here we cannot see anything yet. Okay.
Junoi?
Yes, I also have a very small comment. So sometimes when we compare the mode amplitude with solar cycles, maybe this is a little bit misleading, because for classical Rossby waves, they most happen in equatorial area. For high latitude modes, it's above 60 degrees. So the magnetic field in those local regions may differ from the sunspot numbers. So I think sometimes maybe it makes more sense to compare directly the local magnetic flux instead of the cycle sunspot numbers. I'm not sure if this is a useful comment.
I had one comment about my lack of finding Rossby waves. Partly it's because I haven't really looked. My data is kind of a mess and I haven't really organized it to look for these M equals 1, 2, or 3 kind of modes. They might be there if I add the images together. I just haven't done it.
Yeah, okay. But because this is V zonal and Rossby mode is mostly in the north-south direction. The flow component is stronger in the V theta. So it's harder to see in V zonal component.
So I also have another technical question. So when you use Mount Wilson or other observations for higher latitudes, I believe B angle play a very important role in modulating the flow structures. So what did you do to reduce or remove the effects of B angle?
Well, I have to calculate the P angles and just try and compensate for it. I mean, that's part of what I haven't done, and I don't know how it would work out.
I don't really like reproject because it's line of sight component. I only take care of the mapping, so I make sure the B angle is correct, like you can see this. But for the projection, I didn't reproject back to get the zonal component. This is just a proxy, and the measurement is like over 3-year window, and it's north-south and asymmetrized. So
but when you project the Venn diagram results to the left side direction, I believe you must have to take into consideration of that.
Yes, this I do. Yes, for this line of sight projection of the horizontal flow maps, yes, I need to take care of the B angle.
Well, even for this one, I'm curious. So how high, what latitude can the Venn diagram reach in this plot? It looks very, it's almost up to 90 degrees latitude.
Yeah, because of the P angle. Sometimes the like P angle is large, then I think it's cover 0.98 solar radii, the Venn diagram analysis.
Okay.
Yeah. So if it's a direct Dopplergram, direct V loss, it's directly at edge. You can see it's edge on this movie. You cannot see it very clearly because here there's a white. You see it doesn't really cover the whole disk in the Venn diagram. There's a 0.02 edge here, there. Before V loss, it's a full disk. So this is the advantage of using direct V loss.
I mean, there's, of course, scattered light correction, which is can be significant, and it's quite variable. So that's something that needs to be taken into account as you get as close as you're showing to the limb there. So I don't know what was done with that issue.
In this analysis, like at the edge?
At the edges, it comes in as a, and I can take it out by looking off the limb. I can see how bright the light is off the limb and use that empirically to correct the velocities interior, but that's a separate step. I don't know whether you've done that or not. V-line.
So that's HMI, right?
Yeah, this is HMI.
Well, you're telling me there's no scattered light in HMI?
Oh, there is, but yeah.
Yeah, so
yeah, but this feature it's a large scale, so maybe scale light may make it smear, but it's still visible.
yeah. I would worry a little bit about scattered light as you get that close to the limb.
Okay.
Okay, thanks, Liang. We go to the next talk, another invited talk by Boyang Ding. Boyang, are you there?
Yeah.
Okay.
Can you see my slides? Can you hear me okay? So hello, I'm Boyang. I'm a physics PhD student in Stanford University. And thank you so much for this opportunity for me to talk about our work on the high latitude m=1 inertial modes. So because we've just heard a great talk from Zhi-Chao, I'm going to skip my background section. So just to recap, what we are looking for is the high-latitude inertial modes with mostly m=1 and frequency around -86 nanohertz relative to Carrington rotation rates. And these modes are mostly observed above 50-degree latitude. And the method we are using in this work is using spherical harmonic decomposition to observe this mode in east-west subsurface flow fields, V latitude, V longitude. So let me start to talk about our data preparation. The data we used in this work is STO HMI time distance helioseismic pipeline for the depth of 0 to 1 megameter depth. And our data set spans approximately to plus or minus 80.4 degree latitude. And we cover a time range of more than 14 years. Instead of using the Carrington rotation maps, we retracted using a local rotation rate at around latitude 65 degree, so that you can see on the picture on the right, when we do a spherical harmonic decomposition in the next step, we for each of the synoptic maps, we have the full rotation of this pattern in each page. Oops, sorry. So we also did remove the running average of the maps. So it's like we removed the m=0 mode signal. We also did a progressive Gaussian smooth. Yeah, so to proceed, we did the spherical harmonic decomposition on each of the synoptic maps. And here on the top left is the power distribution of this mode on L and M. And we proceed by doing a Fourier transform on the time axis so that we can get the frequency components. And shown in the middle is the m=1, and on the right is m=2. So we can already see that without any filtering, the m=1 has a much bigger power than the m=2, and the m=3 is almost negligible. Next, we applied a bell-shaped filtering on the frequency and also on the L. We applied a box filter on M to select only the m=1 mode. And then we did the inverse transformations to revert the data back to the latitude and longitude domain. This is an example filtered mode pattern. To better see it, we projected it into the polar view, and here is a video of it. So from the video, we can see that this characteristic yin-yang spiral pattern, it stays stationary for a while, and then it suddenly dies out, and a new pattern will form, but not in the same position, but slightly rotated. And we call this a phase jump. So essentially, this mode packet has a lifetime. To better visualize it, we concatenated all of the synoptic maps along the time axis to further investigate its time evolution. And we squared them to get the power, and it's shown in the plot below. And we separately through the North Hemisphere and South Hemisphere. In this plot, we have the mode power in panel A, and of the North Hemisphere. We also plotted in panel B the magnetic field butterfly diagram around the same latitude range. we can see that in the shaded period of the quiet sun, the mode power is very strong. And in the active period, the magnetic flux surge to the higher latitude. And when it's like, when there's a flux surge, the mode power is strong and mostly uninterrupted. So this is also better visualized in plot C, where we average the panel A and B in some latitude range and then plot it over the time. And we can see some nice qualitative correlations and some peaks that are corresponding to each other. This is suggesting that we might have like the magnetic flux boosting the high latitude modes. And this is in a very nice agreement with some simulation papers, for example, Digbuddy et al. 2024. We further compared it with sunspot numbers and the zonal flow, which is the running average that we removed in the data preparation stage. And we can see this nice anti-correlation as well from the mode power and both the zonal flow and sunspot numbers. Here are the results for the south hemisphere. And we can see that the results are all similar. So we see this chunk of stronger mode power in the quiet sun period. And we also see some nice correlated peaks of the mode power and the magnetic field. What's more, we also see this nice anti-correlation between the mode power and the zonal flow and sunspot numbers. Next, we go ahead and calculated the phase velocity of this pattern and decomposed it into the zonal component and meridional component. So this is basically showing us how the pattern, the spiral pattern moves. And we see those big peaks on the times where we saw the phase jumps at the video. So to better quantify the results, we average over the entire time period for the north and south and zonal component and meridional component respectively, and got a plot we have here. For panel A and B, we see the zonal phase speed of this pattern on the north hemisphere and south hemisphere respectively. Notice that we have a very small difference. It's around only 6 meters per second. And this tells us that this pattern mostly moves rigidly instead of following the sun's differential rotation. We also see from panel C and D, the meridional phase speed mostly are positive for the north, negative for the south. So it is mostly polewards and below the 60 degrees latitude. But then there is a shift of direction at 70 degree-ish, and then showing equatorward instead. However, this meridional phase speed is a composition of the meridional flow and the mode's dynamic itself. So we cannot draw a solid conclusion on whether this can tell us anything about the meridional flow. So next, we calculated the phase differences between in the north and the south. Basically, we selected one horizontal line of data from same latitude north and south and compared its phase differences. And with an average over the latitude range, we see that in panel B, this curve mostly fluctuate around pi, suggesting that the north and south are mostly antisymmetric, but with significant differences away from pi for like some extended periods. Okay, that's all I wanted to talk about. So in summary, we characterized the m=1 mode using time-distance subsurface flow field maps. And we noticed that it might show very interesting correspondence of the local magnetic field and the mode power. We also noticed that it has a very weak differential rotation, and its meridional phase speed shows a reverse of power around 70 degree. That's it. For more details, welcome to check out our recent publications. Thank you. Sorry, Masumi, we cannot hear you.
You're muted now.
Oh, sorry. Thanks, Boyang. And it's open for question. There are time for a few questions. I have a question. If you go back to your meridional circulation, meridional flow plot, yes, this one. So, in both hemisphere, slight, very small tendency of reversal in both hemisphere near the pole. Is that
Here yes, around 70 degree-ish
South Pole?
latitude.
Yeah. Okay. And in the South Pole near the polar region, you are getting a reversal, right?
Yes, yes.
Is this time average or it changes with time?
So this plot is the time average plot. So it's the entire period. So we haven't looked at its a fluctuation a long time, but it certainly has a very big fluctuation. As you can see, this plot has like very big peaks and troughs.
Thank you. So other questions? Gustavo?
Thank you, Boyang. It's possible to compute the Reynolds stresses from this figure that you just presented.
Okay.
Just multiplying the two of them, I believe.
So for the this work we used the east-west flow. So it's because for the north-south flow, we don't have such good coverage up to the that high of a latitude.
Okay.
But I believe Junbei has an idea of somehow processing the data and using and some further ideas along this line. Yes.
Thanks.
Other questions? We have still few more minutes time. If anyone wants to bring an issue.
How did you estimate the error?
So which plot are you referring to? Like this one?
Liang, you are muted.
Yeah, the error in these curves.
I believe this was because we average over the time, so that we have the data to compute its standard error.
Okay, and the error in the previous plot,
Yes.
here.
So let's see Oh, so this one is because we have an average over the latitude range, and we calculated the standard error with that range. Yeah, thank you so much for your question.
So this variation, you can see some variation in the curves, and they are bigger than the error bar, like small variation, like 2-year variation, etc. Do you believe that?
So which ones are you referring to?
In these curves, you can see some variation in like 2-year period, for example. There are some in the red curves, for example, the panel C shaded area.
Yeah. So for panel C and panel D, the mode power is a branding average over it differently. So for part D, in order to compare it better with sunspot numbers, we did like a 13-month shifting window to average it. So that's why like the variations are smoothed over. But yeah, I agree. If we want to see like a more long-term trend, then we probably want to trust like the more smoothed curve.
Lucas?
Thank you for the talk, Boyang. I just wanted to make sure the meridional flow that you showed up, is this just the after the filtering of the m=1 mode?
Yes. So this phase speed we calculated only from the filtered data. Only the m=1.
So probably if you add up everything, you probably won't get this reverse cell at near the poles.
Well, because we haven't like really done the for higher M, so I'm not sure, but it's an interesting point.
Thank you.
I think you'll see that, in fact, that reverse flow is there. It shows up in my analysis as well. Just done rather differently. The same result comes out.
Amazing.
That's great. If you do you have anyone have any other question? If not, then let's move to the lightning talks. And thank you, Boyang. Very nice talk. Our first lightning talk is by Krishnendu Mandal. Krishnendu, are you there?
Yeah.
Okay.
Let me share my screen. Do you see my screen?
Yes.
So today I will be talking about the detection of the inertial modes in the deeper layers of the sun. So all the previous talks, so there are a few questions in the first sessions, like can we detect these modes in the deeper interior, like we like Timo's and Lauren Mongsomi and Gustavo's talks, they try to understand like why, like can we find any, like can we find these modes in the deeper layer? Like some of the questions we can answer by detecting these modes in the deeper layers. So, but the previous observations, they are primarily confined to the solar surface. So, but our analysis, like we will be detecting these modes. So we will be trying to detect these modes in the deeper layers. So for this, we will be using the mode coupling measurement. So mode coupling measurement is the like coupling between Doppler velocity, like in the frequency and the spherical harmonic domain. Like this is ENLM, radial order, harmonic degree, and azimuthal order. So we will be measuring the coupling between different frequency bands and different harmonic degree and azimuthal order. So in this slides, you will see like depending on the coupling, like delta L equal to 0, delta L equal to 1, delta L equal to 2, and delta L equal to 3. like we can detect this mode. So these are all like a different coupling measurement, but in all the coupling measurement, you can see the Rossby waves. So this is delta equal to 2. I added it later. Like this is using analysis of from the analysis of 2 years of HMI data. And if we plot this, so this result is shown only at the surface layer, like 0.98 solar radii. But this is the plot that I am showing that dispersion relation of Rossby equatorial Rossby waves in the deeper interior, like from 0.98 solar radii to 0.80 solar radii. Like as you go in the deeper layer, like you will see that background noise is increasing, like that is expected. So, but you can still see like the low latitude, low azimuthal order Rossby waves, still 0.80 solar radii, like up to m less than 10. So this is the same plot. I'm showing only the frequency in the frequency domain. So at different depths, so this is 0.85. It is the middle panel is 0.8 and the last panel is 0.7. Like you can see that even at the like base of the convection zone, we can see like M equal to 1 and M equal to 3 Rossby waves. This is the high frequency retrograde modes. So this is the hands-on modes that we are discussing previously. So this is like M equal to minus L plus 1, and so this is very weak mode. So that's why I have analyzed it. Like what I am plotting is that power to the like amplitude to the 4. So if we can see like the modes between so these modes for harmonic azimuthal order 7 to around 18. So but this modes like is confined to the surface, like as you go like 0.9, like it is completely noise. So that's why we do not see these modes in the deeper layers. So this is the high latitude inertial mode with M equal to 1. So what I am plotting here is the like harmonic degree and azimuthal order equal to 1. So I am plotting the power for different harmonic degree. You can see like that this is a clear signal between different depths. So 0.98 solar radii, 0.8 and 0.7. So you can see these modes like high latitude mode like in the interconvection zones. Then this is the high latitude mode with M equal to 2. So this is a bit noisy. So 0.98 to 0.7. Still you can see there is a power. So this and the dash line is minus 160 nanohertz. But you can see so this power is around 170 nanohertz. But as we go deeper, like I see there is some changes in the frequency. Like so between 0.98 and between 0.7, like there is a changes in frequency of this mode. So this is my conclusion. Thank you.
Thank you, Krishnendu. Questions? Lucas. No, Lucas is clapping.
Peter is raising the hand.
Peter is writing something.
Raising the hand.
Oh, raising hand. So Peter, please. No, you are muted.
Yes, I got it. All right, can you go back to your plots? I'm confused by your plots. You've got
Which one?
On the all of them. Oh, you got on the horizontal axis. You go in even wave numbers, but you're talking about even the intermediate ones. But my understanding of these plots is that it's like you're only measuring the even wave numbers, but that doesn't sound right to me. Can you explain?
So okay. So these are like so depending upon the different coupling measurement, like we can detect even azimuthal order of the modes. And
are you averaging adjacent wave numbers together?
No. So this is like for this measurement, delta L equal to 0, we can only measure the odd harmonic degree. So there is a selection rule. So depending upon that, like you can only measure the like odd harmonic degree or even harmonic degree. So if we measure delta L equal to 1 coupling, then only we can measure the even harmonic degree. And if delta L equal to 2, we can only measure the odd harmonic degree. So level is wrong because it would be only the odd numbers. But
Yeah. Okay.
Okay, thank you. So we move to the next lightning talk. Thank you, Krishnendu. So our next lightning talk is by Oana Vesa. Oana?
Okay. Hi, everyone. Sorry. Okay. So, and let me do this. Okay. So in this study, we use radial vorticity data from both ring diagram and time distance helioseismology from multiple depths to investigate the potential tilt of Rossby waves. And in this presentation, we're only going to focus on ring diagram data for time constraints. But so a lot of people are familiar with power maps as a standard reference for Rossby wave identification, which you can see in the top row, plotted for multiple depths. And instead of showing the classical dispersion equation, the Rossby wave ridge here is bounded by these dashed lines, which has a width of plus or minus 30 nanohertz, which will be used later. The second row shows the cross power. So this is the joint power between a reference layer and some subsequent deeper layer. And then the third row is the coherence between the same layers. So this is essentially the cross power divided by the power at each depth. And what we can see is that while the normalized power and cross power spectra remain relatively consistent across these depths, the coherence exhibits a really significant variation. With increasing depth, the coherence becomes really distinctly enhanced along the expected Rossby wave signal, while maintaining a low and incoherent signal in the background. So the strong coherence pattern supports that the signal from the Rossby waves is coherent across depths, and then any resulting phase shifts across depths should be systematic rather than noise. However, to avoid interference from the FFT, which introduces a temporal variation in the phase differences, we will first investigate phase differences after in the spherical harmonic domain. So to avoid leakage, we first filter the Rossby wave signal with a filter of width plus or minus 30 nanohertz in FFT space. And then we invert back to real space, spherical harmonic domain space, and then extract the phase difference information from the spherical harmonic decomposition. And we can do this because the complex conjugate of the spherical harmonic function introduces this time-dependent phase and amplitude that reflects the longitudinal structure of each mode. And by analyzing these complex coefficients, we can examine the azimuthal structure or tilt of Rossby waves between some reference layer and subsequent subsurface layers. So panel A shows the filtered normalized phase differences between a reference layer and deeper layers integrated over 15 years. Panel B shows the normalized phase differences for select M's as a function of depth. Error bars are standard error measurements from 1,000 Monte Carlo noise realizations. And what we find is that the normalized phase differences become more negative, with depth suggesting a systematic tilt for Rossby waves. And this inferred depth tilt also varies across modes, with some exhibiting larger phase differences than others, which might point to some mode-dependent sensitivity. But overall, with increasing depth, we find systematic negative phases. We can also investigate the temporal evolution of the normalized phase differences as a function of time for select M's. We chose these M's, M6 through 11, because they have the largest cross-power amplitudes. This data is obtained by segmenting the 15-year data into 3-year chunks with half a year overlap. 13-month smooth sunspot numbers are also shown. So this provides some information on how the tilted structure of Rossby waves evolve with the solar cycle. So we find that while phase differences remain relatively small across the solar cycle for all M's, they exhibit a depth and solar cycle dependence. With increasing depth, we find that the normalized phases become progressively negative, particularly at solar max. During solar minimum, they become less negative, they become jumbled and incoherent. While not shown, the power and cross power during this time is extremely low, and so these phases are not reliable. So the phases during solar minimum are not that reliable. However, as we enter in solar max, we can see that phases start becoming reorganized again, exhibiting that depth dependence. So what we find is that the physical scenario that emerges is that Rossby waves show a westward tilt with depth. That is, the deeper layer leads the shallower layer in the rotational direction, and then this tilt becomes more pronounced westward during solar max. And that's all.
Thank you, Oana. So we can go to the next speaker and hold all the questions for lightning talks in the discussion session. Our next lightning talk is by Roger Ulrich. So, Roger. Roger.
Sorry, I was muted. And
Okay.
now I have to find my talk. Is PowerPoint. Okay. And hopefully I can share this. Do you see it or do I?
Oh, not yet. So you first click that upward arrow in the green box and then select your slides.
I don't see a green arrow in the box. I saw it earlier, but now I'm having trouble finding it.
So you succeeded during the break. So at the bottom, you see that green box that has an upward arrow.
Yeah, okay.
Click that one and then select your slides and click share.
Yeah, now I don't see my slides on this. Click share. I thought I had it. Oh. So, completely.
We can see your screen, but not the slides yet.
Yeah, I know. It's not quite sure where I put the slides. Something like this. So is that showing up?
Not yet. You have to double click that PowerPoint PPTX.
No, I don't see it. I share. Sorry. But I used to just
maybe stop your share, Roger. Open the PowerPoint and then share again.
Raja, if those are the slides you sent me last week, then I can also share for you. Oh, okay, great. Yes, we can see now.
Okay, I'm sorry for being such a klutz at this. At any rate, I wanted to show the time dependence of the solar surface flows. And this is a new way that I've developed for getting rotation rates out of the Dopplergram and magnetograms. The left-hand figure is the magnetogram, and the right-hand figure is the Doppler line of sight velocity as a function of the sine of the central meridian angle, delta L. And it's for this 4-degree wide band going at a particular latitude, which is 20 degrees south, 16 degrees south. And what I do is I fit a quadratic function to all of the individual pixels that I see in this band. They've been punched out because of magnetic fields, but then I get this alpha, which is the meridional flow velocity, and beta, which is the shift in the rotation rate velocity from this one quadratic function. And I think it's a good way to go. I have the A values going from 1965 or so up till the most recent ones when the machine at Mount Wilson died. And in 1983, John Boyden redid the calibration process so that prior to 1983, most of the scatter was from the determination of the calibration coefficient. And after that, the individual observations show the variation that you get from the supergranulation. We do see as you go forward, there are some variations, jump here, which I'm not sure about, but maybe it's real. But the overall pattern of the A coefficient going up and down, I think is probably from the sun. I wanted to comment on the Dopplergrams and the effect of supergranulation. You can see these patches which are oriented kind of towards slices of circles, with the center of the disk being the place where they're all pointing, if you could sort of extrapolate in that direction. So that's the effect of supergranulation. That's the big pattern which is there, and there may be some way to extract the giant cell velocities from these. I mean, it kind of looks like there's some patches of red and others. But I did want to point out the magnetic field effect, which is quite strong. It's what I refer to as a downdraft. Wherever there's a magnetic field, regardless of the sign of the magnetic field, the material on the sun tends to sink. And I think that's a real effect. And consequently, I avoid regions which have a strong magnetic field over 30 Gauss. This is another example showing how the downdraft effect shows up. You can see the strong magnetic fields here, and the intensity is reduced because of the magnetic fields, and the velocity is receding in those regions. So that's why I punch out the magnetic fields. I wanted to show the result of analyzing all of these data points in 6 Carrington rotation averages. And on the left, these 6 Carrington rotation averages have been subtracted. So these are deviations from the long-term average. On the left, you see the torsional oscillation velocities. The zonal velocities are parallel to the equator, sectoral are parallel to the meridional flow. And what you see is that, in fact, I drew the dashed white lines just by eye down the middle of the maxima and the torsional oscillation speed, and just transferred them over to the sectoral velocities. And you see that they line up rather well, not perfectly. There's an offset places, so that the time of the maximum of the sectoral velocity of the meridional flow is slightly offset from the maximum of the torsional oscillation velocity, but they're really, I think, part of the same physical process that's going on, which I don't fully understand. This is just to
Roger, 1 minute.
okay. This to show that the speed is high at high latitudes. The magnetic field is high at high latitudes. These were supposed to be gotten rid of. This is the main result which comes out of this, and that is the meridional flow at both the south and the north high latitudes. These are individual 4-degree bands. They show a very clear and strong up and down effect with the meridional flow coming towards the equator when it's negative and going towards the pole if it's positive. And these two line up rather well. I did a quadratic fit to get the times of minimum. And you can see that at all the different latitudes, both the south and the north, we have a strong pattern, which is very closely connected to the official sunspot minimum. It's a little bit after that. So anyhow, I don't know what's going on. The meridional circulation and the magnetic fields are closely correlated. This is the meridional flow as a function of time. This is the rotation rate deviation. And this is the magnetic field variation at different latitude ranges. So I don't really see any flow patterns besides the torsional oscillations. The torsional oscillations are really quite dominant over all of these things. And if there's a dynamo field that's going on, it should show up in this panel here. So I don't know where the dynamo velocities are. I do know that there's torsional oscillations all the time, but I don't know about any flow in the meridional plane that is associated with the magnetic field variations. So that's what I have to say.
Thank you, Roger.
Okay, I hope I came in.
Thanks to all speakers of this session. And now we move to group discussion.
Okay, so I'll stop my share now.
Yes, and so we please bring up any question. So to start it, I have a question to all the speakers of this session and also to speakers of the previous session and to the audience. What are the observational diagnostics for distinguishing Rossby waves and large-scale flows? Like, well, this is Rossby waves and this is large-scale flow. What are the observational diagnostics to distinguish that?
I'd love the answer to that question.
Yes. Anyone? So
I would say like it depends on the frequency. Like for the large scale flows, like differential rotation meridional flow, their time scale is very long. Like they varies of the order of 11 years. But for the inertial waves, they varies like their frequency like is of the order of few months. So this is the difference. Like for the large scale, like inertial waves, their frequency is quite high compared to the large scale flows.
Also,
Thank you.
at least for the equatorial Rossby waves, when you plot in frequency versus L equals M, right? The observed power ridge matches the classical dispersion equations for these Rossby waves.
Thank you.
And especially the eigenfunctions are important.
So eigenfunctions, like what are the distinction?
Well, we have linear modules that gives us, eigenfunctions which we can compare directly with the observations. So in a lot of cases, there's no doubt whatsoever what we're looking at.
Thank you. Other questions?
Yeah, I have a question to Krishnendu. So you look at the modes for at different depths. You basically only show the power distribution. So I'm wondering whether you have examined the phase differences between different depths, just like what Oana showed previously.
Yeah, it is possible, but I have not done it. Yeah, so it is possible. So we can get the full velocity profile for the entire depth, like the TD flow of the different waves, and then we can measure the correlation between different depth and measure the phase of the inertial waves at different depth. Yeah, it is possible, but I have not done it.
Gustavo?
Yeah, question for all the observers. You are observing the M equal 1 mode, mostly. It has a lot of power. What about the latitudinal order? Ding, Petro, Ding et al., they go up to L equal 20. What about the others? So is 20 the highest order that can we get, or can we go further?
So I can see up to L equal to harmonic degree up to 15 for azimuthal order M equal to 1. So yeah, it depends. For M equal to 1.
Ankit?
I just wanted to say something in support of what Laurent said. Basically, the inertial mode spectrum is so dense, you can match pretty much any frequency you want. It's very important to actually match it with a computed eigenmode to know that it's a real eigenmode that you're seeing.
Junai?
Yeah, I think have one question and some comments. The question points to Zhi-Chao. So Zhi-Chao, in your presentation, you showed the M equal to 1 mode in northern and southern hemispheres, and you said that they showed very good anti-symmetry in terms of phase. And also, Boyang showed in her presentation that the modes are close to pi, close to anti-symmetry, but not quite. So I'm wondering, Zhi-Chao, if whether you have made careful calculation of their phase difference between the northern mode and the southern modes, or is it just a visual inspection?
To me, it's a global mode, so there's no northern mode and southern mode. It's a global mode of oscillation, so it's the same mode to me.
So I think when you look at the data, you look at the North Pole and the South Pole separately.
Then, because in the spectrum we can decompose into north-south symmetric and anti-symmetric.
I see.
And if we only look at the North Pole without symmetrization, then it's like a beating between like the linear composition of the two symmetric components.
No, okay, got you.
Maybe I can
So
I can comment a little bit. Or...
Yes, please.
Yeah. So basically, if we assume that the rotation of the sun is north-south symmetric, then we will end up with two modes. One which is north-south symmetric, and the other one that's north-south anti-symmetric. They are both global modes. Now, of course, and they have frequencies according to theory that are very close, very, very close. So there could be some beating here. But of course, the rotation of the sun is, we don't know exactly if it is north-south symmetric. There could be a little difference between the north and the south. And that would lead to two modes, each of which, would not be either purely anti-symmetric or symmetric. Yeah, we need to know rotation to be able to answer that question, I think.
Okay, thank you. So here's my comment. So from Boyang's presentation, we saw that the North Pole and the South Pole modes, they are mostly anti-symmetric, but sometimes they diverge from the anti-symmetry. But after a very short time, for about 1 year, they are back to anti-symmetric. So I think it looks like there's some mechanism controlling these modes very, very far away from each other. So anyone wants to share any thoughts about what controls this beating of the modes in two hemispheres?
I don't think there's a mode per hemisphere. This doesn't work this way. You cannot split hemispheres, right? You may have two modes that have very close frequencies, both being global.
Yes. And very close frequencies and a slight difference will create that beating.
But doesn't this require that the differential rotation or the rotation is exactly the same at both hemispheres?
I think the upwelling from the poles, which I show in my plot, is very well coordinated between the North and the South poles, is a big puzzle. It indicates that there is something flowing upward at both the North and the South poles at the same time, and then flowing out towards the equator during that period. And it could be some sort of circulation at the tachocline that is globally symmetric and going both ways and causing an upwelling at the poles. But I don't see any way to avoid something is coordinating the North and the South Pole time dependence. They're just too close.
Yeah, that's what these modes are doing. Yeah.
Okay, I think we have used our discussion time. Now I transfer it to Gustavo, I think, for overview. Or who is doing the overview? Gustavo, you are doing the overview.
Yeah. So just let me use share. Can you see my screen?
Yes.
Okay. So first of all, I'd like to thank all the invited speakers and all the speakers that give the contributed talks. This was very nice workshop. It was short and it had a lot of information. Special thanks to the people that are in Europe, for whom now it's pretty late, and they are still here discussing and sharing thoughts with us. So I kind of was writing some concluding remarks, and please let me know if I'm wrong in my conclusions, but this is what I was taking from the sessions that I was hearing. So starting with, we have done great advances in both fronts, in the observational and in the theoretical modeling of the inertial waves. We have linear models and we have nonlinear models that are able to reproduce most of the inertial modes that we see in the sun. So we reproduce the polar vortex, and we reproduce the Rossby modes, and we also hear that it's possible to reproduce or convection simulations find the high frequency modes, right? So probably we can get to a stage where we can infer some parameters from the solar interior, like turbulent viscosity or subadiabaticity or adiabaticity. Yet we have to still be cautious on this, because this requires high numerical precision and requires very good fine-tuning of the parameters of other parameters of the solar interior, right? So we have to get very well the position of the tachocline, thickness of the tachocline, and we also have good results on that. So probably we can get very nice results from Rossby waves inferring things that we don't know about the solar interior. We heard about thermal Rossby waves, and these are the banana cells or something like this, and these are a big mystery. They might be needed to reproduce the retrograde high frequency modes, yet the prograde modes are not observed. So what is happening? We still don't know, and this is when we don't know something, this is food for thought, right? So we have more work to do, and we can understand what this is telling us about convection in the sun, and we can think if this is connected with the convective conundrum, right? So I remark here Peter Gilman contribution that perhaps that the energy of convection is maybe taken by inertial mode, so that both kind of motions are in equipartition. Perhaps this is what's happening. Also, it's very nice that we have great consistency in measurements from inertial modes between different instruments, right? Yeah.
Sorry, it is Gong. It's not SDO. Mount Wilson, HMI, and Gong.
Oh, yeah. Oh, yeah, sorry. Let me correct this. So we have very good agreement between these instruments.
Gustavo lost the sharing.
I'm not sharing now? Oh, why not? Yeah. So we are at a very good point that we can get time evolution of these modes, and we can follow the high-latitude modes with time, and we can follow the Rossby modes with time. And if I got it right, high-latitude modes correlate with the local magnetic field, yet they anti-correlate with the sunspot number, and Rossby modes anti-correlate with the local magnetic field. Observations.
Rossby mode is strong. High M Rossby mode is strong during solar maximum. So I would say it's positively correlate with the.
Oh, they are positive correlating. Okay, yeah, thank you for that. I will correct this in a minute. So finally, we can observe these modes even deep down in the convection zone. and then we can be able to check correlations between inertial modes and, for example, sunspot cycle. We don't have measurements of magnetic field, of course, deep down, but we can see how this evolved with the cycle. And we can also look for the tilt of these modes, and we can get some information also from the physics of the convection zone, looking at this tilt. So these are my concluding remarks. I think there is a lot of things that we have done, and there is a lot of things that we can still do. So it's a great topic of research. Again, I want to thank you all for participating, and hope to see you in next meetings on inertial modes. Yeah, thank you.
Gustavo, is it possible to add something?
Yes, of course.
Yeah, so thank you very, very much for the organizers. This was a very, very nice session. I would like to invite all of you, if you have time, to join us in December in Germany, where we will organize, let's call it a workshop. I mean, it's between a conference and a workshop on these topics. And we have reserved the week of December 15 to 19. Very close to Christmas, but that's the only time we could find.
But that's the AG week.
Okay, well, you'll have to choose.
This will be in Göttingen?
Yeah, no, it will be in Berlin. It will be in Berlin, with a very nice venue for this. And I will send details. We may also have some funding, so if some of you are not quite sure how to travel, we could possibly help.
Yeah, can you share the link in the chat, please, to this workshop?
There is no link yet, but
okay.
Right, December.
Laurent, are you allowing virtual?
Sorry?
Are you allowing virtual?
Am I?
Virtual or fully in person?
I don't understand.
Virtual, online. She's asking, are you allowing
no,
virtual?
it's in person. It's in person, yeah.
Okay.
December in Berlin, and the place is Harnack House.
Oh, Harnack House, fancy.
Yeah. It's a fairly nice place. So maybe Ankit knows it. Okay.
So should we write you to get more information?
Yeah, as soon as I have more information, of course, I will send it to you. Yeah.
Okay, thank you. So I believe we can close this workshop now. It was a really good time. Thank you again, guys, everyone. Thank you to the other organizers, Wei, Mausumi, and Oana. It was very nice working with you organizing these meetings.